All right, so let's talk about nuclear fission and nuclear fusion. Okay, so I'm gonna grab my pen. Go with blue this time. There we go. Okay. All right, so fusion, like we said in the last video, fusion occurs when you have two nuclei combining to make a heavier nucleus. So the sun is a fusion reaction, or is a fusion reactor. All stars are fusion reactors. And the biggest reaction going on in the sun is thought to be the one right here in front of you. And it is the combination of two isotopes of hydrogen to make one atom of helium, a free neutron, and a bunch of energy. Now, both fission and fusion release a lot of energy, but something to know is that fusion releases more energy than fission. So the fusion that occurs in the star is releasing greater amounts of energy than the fission that we perform in, say, an atomic bomb or in a nuclear reactor. So just to have a visual for what fusion in stars look like, you start with, up here at the top, we have, this would be step, wow, we could spell. Step one, we have two hydrogen atoms that are fusing to form an H2, all right, which is actually involves the change of a proton into a neutron, which is allowed. You just have to have some energy expenditure and give off a neutrino and give off a positron, and that's upper level stuff, right? But we are going from two hydrogen atoms into an H2 isotope of hydrogen. It then is going to combine, wow, I did it again, step two, there we go, with another hydrogen atom. Another gamma ray is going to be released. We end up with helium-3. So I have proton, proton, and a neutron. And these two helium-3 in step 3 are going to combine. They're going to release a hydrogen nuclei, right, H1, and they are going to be left with a regular helium nucleus. And these two hydrogens go back and are recycled and start the process over and over again. Something to think about with stars, right? Stars are really, really, really big. They're really, really, really massive. And the gravity of the star pulls all those atoms closer and closer and closer to the middle. And the cool thing about a star is that the gravity is so great in the middle that this reaction proceeds because the weight above them, the mass of the atoms above them pushing down on them, get these initial step one hydrogens, right? These guys right here. It gets them so close together that they start to touch, and that's when you get your reaction. So pretty cool visual there for how fusion takes place in the stars. Well, let's look at fission. Fission is a much more down-to-earth reaction. We do that one here. And it is when you split a heavy nuclei into two lighter nuclei. And there are some elements, the radioactive elements, that undergo fission spontaneously. You can bombard a normally stable element with another particle in order to make it undergo fission. When we talked earlier in the year about the fact that James Chadwick discovered the neutron, the way he did that, he used alpha particles from polonium, which is a radioactive element that Marie Curie discovered, and he used those alpha particles to bombard beryllium atoms. So like he used alpha particles like bullets and shot the sample of beryllium. It cracked the beryllium open and it forced the emissions of neutrons out. He detected those neutrons, and that's why he is responsible for discovering the neutron. So what does fission look like visually? Well, so if you look at uranium, uranium is a pretty well-known radioactive element. You can cause uranium to undergo fission by hitting it with a neutron. And when it does that, it absorbs that neutron. The neutron-proton ratio, right, in that belt of stability we talked about earlier, is way off with that extra neutron. It gets unstable, and it starts to kind of vibrate like this, and whoosh, it splits apart. When it does that, it releases a lot of energy. The nuclei are not split evenly, so you get a krypton which is number 36. That's 36 protons. And you have a barium that comes out, which is number 56. And it also gives off 3 more neutrons. Okay, so that's what we're looking at here. Neutron on the left plus uranium gives you krypton, barium, and 3 neutrons. Now, the 3 neutrons right there are the important thing, because if you have a lot of uranium in one place and you start to give off a bunch of neutrons, these neutrons kind of recycle back and can split other uranium atoms, which will release even more neutrons, which will cycle back and start again. And so an atomic bomb works on that concept. When you are splitting these atoms, they're giving off these extra neutrons. They're going to run into other uranium atoms. They're going to undergo fission. They're going to release neutrons, so on and so forth. And the result is what we call a chain reaction. Now, chain reaction is pretty easy to, is not always easy to start. You have to have things lined up just so. But once it gets going, it's very difficult to stop. So if we look at this little animation here, we can see that this neutron is absorbed by U-235, right, our uranium-235. It becomes unstable. It splits. When it splits, it gives off these other neutrons, and that's bad news for any uranium around them. So if we look at it like that, we can understand that, hey, this is not necessarily a real difficult piece of chemistry to understand. Now, in order to get a chain reaction, you have to have enough uranium all in one spot in order to, and oriented in a way that those released neutrons will interact with those other uranium atoms. But if you get that just right, what we have is called critical mass. And that is the minimum amount of fissionable material you need to sustain your chain reaction. You don't want it to just fizzle out. You want it to actually keep feeding itself and grow. If you don't have the critical mass, you have like a dirty bomb. It releases some radiation, but it's not a true atomic bomb. If you do have critical mass, though, you get the characteristic atomic bomb. Now, we can kind of see this in a chain reaction if we look at it like this. So neutrons come in, and as they split more and more and more, the reaction goes faster and faster, and we release more energy all at once. And the more energy release in a short period of time, well, the more devastating the bomb is going to be. Okay, so this is kind of your visual for a chain reaction. So 2 to 4, 4 to 8, 8 to 16 to 32 to 64, so on and so forth. Now, as far as what an atomic bomb looks like, I just think this is interesting. It's not actually a very sophisticated device. You have a wedge-shaped piece of uranium, and it's aimed at 2 other wedge-shaped pieces of uranium, and there's a dynamite plug in one end, and when the dynamite explodes, this goes rushing that way, and you mass the 2 together, and those 2 subcritical masses become a critical mass. Now, something that's bad about an atomic bomb that I'm sure you're aware of is something called fallout. And fallout is the irradiated dust, the irradiated particulate that falls out of the atomic cloud, right? The mushroom cloud. And it's going to remain in that area after a nuclear event for a really long time. Some ways that can be bad for people or animals is inhalation. If you eat it, like if the dust is on some of your food, if you drink water that's been contaminated, there's many different ways. There are many different ways for you to be exposed to this. And if you are exposed to many sources of irradiation, you can actually develop what's called mass access cancer, which means you get a bunch of different cancers all at once. Now, if you're interested in some of the Cold War bombs and some of the larger atomic tests that we've done, you can check out some of these links. I'm not really going to go into them, but one of them that's really cool is the Tsar bomb, the biggest bomb ever dropped, right? It was dropped by the Soviets. Now, back to radiation sickness and mass access cancer. So radiation obviously can cause issues. If you ingest or inhale or otherwise take irradiated particles into your body, you can end up with cancers. You can end up with tumors, things like that. You can also end up with something called radiation sickness. If you get acute radiation sickness, you get a very high dose of radiation in a short period of time. You can get burns on the skin, hair follicles can die and fall out. You end up with blisters, things like that. Or you can have chronic radiation sickness, which is when you get many doses over a long period of time. So the acute effects look much more like a burn. The long-term effects, though, are really unique to radiation sickness. Now, we measure radiation using sieverts. That's the SI unit we use to measure radiation. It's not the only unit, but it's one of the most common. And a sievert carries with it about a 5.5% chance of developing cancer. The more sieverts you're exposed to, well, the greater the chances of you suffering some kind of cancerous event. Now, why? Why does this, why do these things go together? So remember from biology that the irradiated particles, right, that radiation, it can impact your DNA. And mistakes in your DNA can lead to mistakes in your cells. And if your cells have mistakes in them, they can become a tumor. They can lead to a cancer event, okay? Lots of different ways that radiation can affect the body. Another fairly interesting unit is called the REM. A REM stands for the Rontgen Equivalent Man. That's the unit. If you've seen the TV show Chernobyl, they talk about Rontgens quite a bit. I believe they say like 3.6 Rontgen, not great, not terrible. It's kind of like a joke. The detector that they had for radiation at Chernobyl only went up to 3.6 or whatever they say. So they were like, oh yeah, we're maxing out our detector, but it's only 3.6. It was actually well above that. But, the detector only went up to 3.6 or whatever, so that's not good. Anyway, one REM carries a 0.05 chance of developing cancer, so you need 100 REMs to equal one sievert, okay? Anyway, if you get greater than 100 REMs in a very short period of time, you will probably get ARS. Now, just to give you some examples of some when you might get a REM exposure, right? These are in millirems, so 1,000th of a rem. So if you get an x-ray on your chest, you get about 10 millirems. So if I have a 10 millirem exposure, and I know that 1,000 millirems is equal to 1 rem, well, then that would be 10 divided by 1,000. Why is my pen not working? Hold on, thought, just a second. My pen has died. Let me restart my tablet here. Hey, there we go. 0.01. There we go. So I would need 100. All right, this is 100th. So 100th of a rem. I would need 100 chest x-rays to get 1 rem. So I would need a lot of chest x-rays to get greater than 100 rems, right? If I looked at, say, a full body scan, that's 1,000 millirems. That's 1 rem. So I would have to get 100 full body CT scans in order to have a greater chance of getting acute radiation syndrome. So going to the doctor, getting a scan, not necessarily a bad thing. Here's some more interesting facts just to look at about radiation. So the NRC is the Nuclear Regulatory Committee, and the dose limit is 5,000 millirems, 5,000 millirems in a year. That's the annual nuclear worker dose limit. Now let's look and see what that is in rems. So 5,000 millirems. You know that there's 1,000 millirems in 1 Rontgen equivalent man. So that's 5 REM, 5 rems. And we know that you have to get over 100 in order to be at risk for acute radiation sickness. So you would need to get the max over 20 years. If you only got the max, it would take you 20 years to get to 100 rem. And so the NRC has a pretty low threshold for the radiation dose. Now, some Interesting things. Here's the average U.S. annual dose for regular people. That's just like going outside, that kind of thing, right? Your body gives you about 40 millirems a year. Cosmic rays from the stars and the sun give you another 30. If you look at the safe drinking water limits from the EPA, you can get 4 millirems of irradiated material into a water source, and it's still considered safe. If you fly across the Atlantic, because you're up high in the atmosphere and the atmosphere is not absorbing as much of the cosmic rays, that'll give you 2.5 millirems right there. So we get a lot of radiation, just part of being alive. It's not necessarily out of the ordinary to have radiation exposure. So some nuclear power plants, these might be images you're familiar with, right? They are certainly well known for providing electricity. You may not know how many there are in the country. There are actually quite a few. But nuclear power plants have not always had a great set of support, we'll say. Even Ernest Rutherford, who discovered quite a bit of, radioactivity, said that, yeah, if you're breaking down an atom for energy, that's not a good thing. You're not going to make much, energy there. He was one of the few things he was wrong about. But this is how a nuclear reactor works. It's pretty simple. It's basically a big steam generator. And so you start over here on the left. This is our containment building. And in the container building is a reactor vessel. And in that vessel, you have two things. You have some source of fuel. It's probably uranium pellets. And you have some control rods. If these are my uranium pellets, they're fuel rods. They're like this. Two fuel rods next to each other. As they decay, they will interact. They will produce heat. A control rod, usually graphite, comes down like so, and it absorbs the neutrons, and it doesn't let them talk, doesn't let them interact with each other, and it prevents the reaction from taking place. So, let's see if we can get rid of that. There we go. So anyway, we have our, I don't want my pen again. There we go. We have our reactor vessel right here. There's our uranium fuel and our control rods. And there's water in that reactor vessel. As the uranium breaks down, as it undergoes its reactions, it generates heat. The water absorbs the heat. It's turned into steam, right? So the steam leaves the containment building and goes to a turbine. The turbine turns, all right, turns a generator, which produces electricity. That water, as it goes through, is then caught in a condenser. All right, it is pumped to our cooling tower. It usually goes to the top, and then it swirls back and forth all the way to the bottom. As it does that, it gives off, there's condensation that forms, and that makes a water vapor cloud, and the water is then recycled right back into our into this steam thing. It actually doesn't go to the reactor vessel. But in other words, it's a big steam generator that turns a turbine. It's not an overly complicated system as far as the overall workings. Now, as far as building one, yeah, obviously that's going to be very complicated. But we're pretty good at it. We have quite a few nuclear reactors in the States. Here are some of them, not all of them, but there are quite a few. You can see that Virginia has a couple. Pennsylvania has some, Ohio has some, Wisconsin, Michigan, Illinois has quite a few, Florida has quite a few, South Carolina has more than Texas does, which is odd. Lots of nuclear reactors. So how does a nuclear reactor compare to a nuclear bomb? Well, first, they use subcritical masses on purpose. That's a safety thing. So even if the core was to have a meltdown, the point is where it won't go critical. It won't explode into a nuclear bomb. The core has control rods in it, like we're talking about. They go up and down in between the fuel rods, and they absorb neutrons. They slow down the reaction. They prevent heat from being generated. They slow the production of steam. It slows the overall production of electricity. If you put the rods into the core, You have less fusion, less steam, less electricity. If you pull the control rods out of the core, well, then you have more steam, more electricity. In theory, as a safety feature, if the power gets cut, the rods fall all the way down to the core, all the way to the bottom, and they shut everything down. In order to get your electricity, the fission heats up the water, kind of like I talked about in another slide. The heat gets carried away by these steam pumps. The steam turns a turbine, generator makes electricity. There we go. There are a lot of really good things about it. It doesn't pollute, right? That big cloud coming out of the cooling tower is just condensation, all right? It can make a lot of energy in a very long period of time. It is a great alternative to fossil fuels, but there are also some cons, right? You have waste products that are radioactive, that are dangerous. If you're going to store that waste, you got to think about the container that you store it in because it could break down. You have thermal pollution. If you think about some of the safety things that have been built into these, underneath the cooling tower, there was a water reservoir. That water reservoir can be shunted into. Usually, you build a nuclear power plant near some body of water that can kill fish. It can kill amphibians, that kind of thing. You do have to worry about theft, right? If someone was to try to steal plutonium or uranium. And obviously, if that was to happen, you could lead to some kind of nuclear catastrophe. And we have had some nuclear catastrophes. Probably the most famous one is Chernobyl. This is one of the very few photos of the, one of the few good photos, rather, of the reactor after the explosion. You'll notice it looks kind of like it's kind of grainy. That's not because it's an old photo. That's because the amount of radiation coming out of this hole right here was messing with the camera, which is, terrifying. And what happened at Chernobyl basically was a long series of unfortunate events that could have and should have been prevented. But basically, in a nutshell, they were running a safety test. They did not follow all of the parameters in order to set up the reactor for the safety test. When they tried to stop the test, the ends, so here's your control rod, right? Well, the end of the control rod had a graphite tip on it. And the graphite tip actually does not, this was bad, it does not slow the reaction in the Chernobyl one. So this graphite tip. And when they tried to put the control rods back into the reactor, they got jammed with just the tips in the reactor. That sped the reaction up, which was not good. It ended up blowing the top of the reactor off, and big fireball, big explosion, lots of radioactivity released into the air, and they had quite the time trying to clean it up. There was actually the risk of a secondary explosion. They sent divers in to kind of mitigate that risk. They were successful. They prevented that secondary explosion, but there was great risk involved with that. There's a video here you can watch about how it worked. Real good video. Give it a look. There's another video about how it detonated, and these are both from the Chernobyl TV show. They're not 100% on, but they give you kind of a pretty good idea of what's going on and a little bit of drama to boot, right? So the radioactivity after the accident was measured and well documented by scientists. One of the things that was released by the Chernobyl accident was cesium-137. Cesium is a radioactive isotope, which is not great for living things. You can see that the darker the red, the worse the color, or the greater the concentration, the worse the outcome. This obviously is the area around Chernobyl. There's Chernobyl right there. So the prevailing winds, right, are going to sweep these debris out over the European continent. So it's important that we are careful with even one nuclear reactor, because one nuclear reactor accident and you have a great number of people that are impacted, in this case, the whole of Europe. Now, one of the more recent disasters we've had has been in Fukushima. And Fukushima Daiichi was a nuclear power plant in Japan. It was damaged by an earthquake and a tsunami. And you can see here these two circles, right? This circle right here and the circle right here. Those are both 80 kilometers. And you can see that Chernobyl had quite a bit, or like if you look at the red, you can see the amount of cesium-137. You can see that Fukushima had similar amounts, but in a much smaller, more focused area compared to Chernobyl, all right, which got these great big red areas in multiple places, which is not great. You can also see over here that Fukushima actually had, as an overall, exposure, much lower exposure of cesium-137, which is a good thing, okay? However, nuclear disasters are part of working with nuclear power. It's something that you have to weigh when deciding, hey, am I for nuclear power or am I against it? So just kind of in, we'll say, contrast to that is the potential for nuclear fusion to be a source of energy. A lot of pros. It's abundant, right? You need hydrogen. You can get hydrogen from water. We have lots of water, so we can have lots of hydrogen. Hydrogen is also the most abundant atom in the universe, so we shouldn't run out. It's clean because it makes helium. That's it. It's not going to be used to make weapons. It's like, here's a bunch of water. We're going to split it with electricity to make hydrogen, and we're going to mash it together. It's not going to blow up. It's not going to run away, right? You're not going to get a chain reaction out of it. One big problem with fusion, it doesn't work yet. We haven't made it work. Carl Sagan was a big fan of nuclear fusion. He had a Spitzer lecture on it. And the thing with nuclear fusion is it's hot. Plasma is like really, really hot. On the in the core of the sun, it can get up to 100 million degrees Celsius. It's high density, which means it is hard to contain. Because plasma, you can't touch it. You have to contain it with some kind of magnetic field, and you have to keep it there, and then you have to spin it so it can turn your turbine and stuff like that. So lots of different problems with getting nuclear fusion to work. Not insurmountable, just things that science is currently working on, right? So here are some ideas of ways that they are kind of investigating that. I like this one on the left. It reminds me of the first Iron Man movie. Go figure, right? Anyway, so that's the video on nuclear fusion. If you have questions, let me know. There's one more video, a little bit more math on half-life and rates of decay. Watch it next.